Welcome to this discussion on Russell's paradox and its impact on mathematics and computing. My name is Farron Mahler, and I am professor in the Computer Science Department at Swansea University. I'm also director of Technocamps and the Institute of Coding in Wales, which are pan-Wales schools and business outreach programs. Now, our discussion starts with this throwaway pun made by a popular comic actor of the mid-20th century. I refuse to join any club that would have me for a member, is what Groucho Marx said. Now, after your first reaction in recognizing the punniness of this statement, its paradoxical nature starts to sink in. Now, if you're not a member of a particularly elite club, then of course you want to be a member. But if you are a member of this club, then you want not to be a member. Now, Groucho Marx, he was just a comedian. He never claimed nor aimed to be a great philosopher. However, with this one pun, he inadvertently hit upon one of the most profound ideas in 20th century logic. Now, the paradox that we're going to explore is commonly seen in the guise of what's called the Barber Paradox. And it's about a village barber, right? So we have a certain village, and in this village, every man is clean shaven, okay? And one of these men is the village barber. Now, the barber, obviously, what's the job of a barber? Is to shave those men who don't shave themselves. So a man wakes up in the morning and he may shave himself. Or if he doesn't, then he goes to the barber and the barber shaves him. So the barber, he shaves all men who do not shave themselves, and he only shaves men who don't shave themselves. Okay? Now the question is, who shaves the barber? Right? Now if he shaves himself, then being the barber, he doesn't shave himself, right? Because the barber only shaves men who don't shave themselves, right? But if he doesn't shave himself, then again, as he's the barber, he must shave himself. Yes. So we seem to be hitting into a paradox. The barber shaves himself and he doesn't shave himself. That doesn't seem to make sense. Now, people don't like paradoxes. I mean, they kind of, well, maybe the barber is a woman. No, we said we're supposing that this is one of the men. Well, maybe the barber comes from a different village. No, we're supposing in this village there is that man who lives in the village who is the barber. Well, then the conclusion is, well, such a barber cannot exist. So it's not really a paradox. It's only a paradox if you really want to insist that there is a man in this village who is the barber who behaves exactly like that, right? Now, paradoxes themselves, they're ancient. I mean, the Greeks had many. Zeno and Aristotle were rich sources of paradoxes. But the closest in spirit to the Barber Paradox is one attributed to Epimenides, who came from the island of Crete. Now, whereas Zeno and Aristotle, they were deliberately devising paradoxes. Epimenides, he was a writer of prose and poetry. Now, he surely would never have imagined that he'd become famous for a single line taken from one of his poems, nor particularly for the reason why this single line made his name, right? So he wrote a poem, and it was about Zeus. And in this poem, he has the character Minos, another person from Crete, tell Zeus, they fashioned a tomb for you, holy and high one, cretins, always liars, evil beasts, idle bellies, but you're not dead, you live and abide forever, for in you we live and move and have our being, right? So he was complaining that the cretins were suggesting that Zeus was not immortal. He was a mortal being, right? And Minos in words given to him by Epimenides, was saying, cretins are always liars, right? But these words to Minos, ultimately we attribute somehow to Epimenides, and we accredit Epimenides with the paradoxical statement, all cretins are liars, right? Now, as Epimenides is a cretin, he's making this statement. He's declaring that he himself is a liar because he's a cretin. Well, if he's a liar, then this is not true. But then comes the crux. It's always misunderstood that this is a paradox. If he's telling the truth, then he must be lying. Okay, so he is lying. So what he's saying is not true. It is not true that all cretins are liars. Right? So what we actually have here is not a paradox. It's oddly a proof of an historical fact. It's proving that at some point in history, there existed a cretin who told the truth. Not all cretins are liars. There is a truth-telling cretin, right? So it's actually mistaken to be a paradox. But that's not really an issue because it's very easy to turn it into a paradox. And the paradox that it is turned into is often credited and called Epimenides' liar's paradox, or just the liar paradox. And there are various versions. The most simple is, I am lying. That's the closest to the original wording of Epimenides, that all cretins are liars. Epimenides said, I am lying. Or, this statement is false. Is that statement false or true? Well, if it's false, it's true. If it's true, then it's false, because it says it's false. Or, is the answer to this question no? Think about it. Right. Now, philosophers don't like paradoxes. Well, they like them and they don't. Throughout history, they've just tried to argue them away, right? Just like a magician's tricks are they're just that. Tricks that give the illusion of magic, but can be easily explained away once the magic is revealed, right? In a similar vein, philosophers and linguists throughout history have sought to explain away paradoxes as mere linguistic trickery. However, ultimately their efforts proved to be in vain. You just cannot escape paradoxes, right? So, for example, one of the objections to the liar paradox is its use of self-referential demonstrative words like I am lying, or this statement is false, right? If you're going to have self-reference like that, then you will get yourself into trouble, and it's just a bizarreness, right? But there are ways around it. A simple first solution is to break it into two statements. And two sentences. The first says, the following statement is true. And the next statement says, the preceding statement is false. Right? Now, neither statement is referring to itself in this way, right? And if you think about it, well, they can't work. If the following statement is true, then that's saying that the preceding statement, that statement itself, is false. But if it's false, then the next statement is not true. So it's true. Again, there's a hidden self-reference in there. But Willard Van Orman Quine provided a very nice rebuttal to this sort of common linguistical dismissal of paradoxes. Right? What he said, let's take the phrase yields a falsehood when appended to its own quotation. And let's put quotes around it and append it to itself. And what you get is this sentence, quote, yields a falsehood when appended to its own quotation, unquote, yields a falsehood when appended to its own quotation. So it's in a way a recipe for constructing itself. Take that phrase, puts quotes around it and append it to itself. So it describes how to build itself as a sentence. And what does it say? It says, it produces a falsehood. Now, if it is true, then it produces a falsehood, and it's false. So if it's true, it must be false. But if it's false, then it doesn't create a falsehood. So it's true. So it really is a paradox in this sense, right? And there are different ways of doing things like this and just getting around any objections that the philosophers and the linguists might have to the idea that paradoxes might exist. They do exist, right? Here's another lovely linguistic paradox. So Kurt Grelling and Leonard Nelson invented this cute idea. They said, well, some adjectives, they're words that describe themselves. So, for example, the word short, you would never deny that that's a short word. Or polysyllabic, that word has a lot of syllables. It's very much polysyllabic, right? So let's call such adjectives autological then. So short is autological because it describes itself. Polysyllabic is autological because it describes itself. Yes. On the other hand, words like long obviously don't describe it. Long is by no means long. Monosyllabic, no, that's made of more than one syllable, right? So it's certainly, as a word, not monosyllabic. Yes. So let's call such adjectives heterological. So a heterological adjective is a word which does not describe itself. Yes? So then the question is, the word heterological, is it heterological? Well, if it is heterological, well, that means it does not describe itself, so it's not heterological. But if it's not heterological, it's not a word that does not describe itself, then it must be heterological. There you go. Another, by the way, interesting paradox, in a sense, is the question as to whether autological is autological or not, right? But it's paradoxical in another funny sense. It is autological exactly if it is autological, and it isn't exactly if it isn't, right? So somehow, if you ask yourself if autological is autological, it's perfectly safe to assume either answer. You can go around believing that autological is autological, or you can just as consistently go around believing that autological is not autological. Neither one of them will get you into trouble. Paradoxes are bizarre and deep and fascinating in this sense. But why are we interested in these things? Well, here's a gentleman. He was around at the turn of the 18th, 19th century, so around about 1900. There are exciting things that were going on in the world of mathematics, as mathematicians and mathematical philosophers were trying to come to terms with the core understanding of mathematics, right? To get to its foundations, right? Up until about that time, mathematics was just like a compilation of disjoint subjects. There are mathematicians doing algebra over there, number theory, topology, analysis, and the mathematicians were happily discovering and proving results in each one of these subjects. But there was this growing concern over the foundations of mathematics. So, for example, with the fast and loose approach that calculus dealt with infinitesimal amounts, right? And the philosophers, they started in earnest looking for ways to set the whole subject on a firm foundation. Gottlob Frege was by no means unseen in this sense. He spent his life thinking about these questions, right? And decades of his life was dedicated to provide a logical basis upon which all of mathematics would rest, right? So for this, he reduced essentially all concepts not least of which that of number, to sets or collections of objects. Right? So a concept, to his mind, corresponds to the set of all objects that fall under that concept. So objects to him were like extensions of concepts. Right? So, for example, the color of blue. How would you define that? Well, blue, to his mind, just corresponds to the set of all blue things that exist in the world. All blue objects, click them all together, and that represented the concept of the color blue. Or the number 3 corresponds precisely to the set of all 3 element sets. Right? So these things are the way in which concepts in his mind were defined and were built upon. And from that, all mathematical facts would be derived using pure logic alone from irrefutable axioms about these objects. Okay? Makes a lot of sense. Right. Along comes Bertrand Russell. Right? Frege had produced large tomes and was publishing this stuff 20 years in the making before Russell comes along and sends him a letter. And in this letter, he says, "Dear colleague, I find myself in complete agreement with you in all essentials. In regard to many particular questions, I find in your work discussions, distinctions, and definitions that one seeks in vain in the works of other logicians." Now, Bertrand Russell was very much enamored by Frege and his work and what he was doing to lay down the foundations of mathematics. And he was doing it in such a precise way that Frege really thought very highly of Frege and what he's doing. There's just one point where I have encountered a difficulty, says Russell. It's not a long letter. And he says, consider the set of all sets that are not members of themselves. Is that set a member of itself? We're going to look at this on the next slide. But when Frege read these words, they sunk in very quickly. And he spent the next 20 years wondering essentially how to solve this problem. And his response ultimately was, my effort to throw light on the question surrounding the word number seemed to have ended in complete failure. So what is it that Russell did? Well, normally a set will not be an element of itself. Right? It's a kind of a little bit bizarre to imagine a set, a collection of objects, being a member of itself, but there's nothing to preclude us considering abnormal sets, sets that are members of themselves. Right? There's certainly nothing in Frege's work, nothing at all in particular that would dismiss the idea of a set being a member of itself. Okay? So Russell said, well then, consider the set of normal sets. Let's call it R. So R is a set, and in that set is every single normal set. Remember, a normal set is a set that is not a member of itself. So R contains every set A which is not an element of itself. Okay? And the question then is, the set R, is it a normal set or is it an abnormal set? Right? If it's a normal set, that would mean it's in R because R is the collection of all normal sets. So R would be an element of R. It'd be one of these sets A, which is not an element of itself. Hold on. You're saying if R is in the set R, then R is not in the set R, because that's what it would mean to be in the set, is if it's not a member of itself. So R cannot be in the set of normal sets R. Right? So R is not an element of R. Hold on. If R is not an element of R, then it satisfies the definition of what it means to be in the set R. So it is in R. So R is an element of R if and only if R is not an element of R. Now, if you're going to produce a foundation of mathematics, it's not very good if you can prove that something is true exactly if it's false. No. So this was the fatal blow to what Frege was doing. Now, Bertrand Russell, of course, he's very much interested in this program of defining the foundations of mathematics, and he carries out his own program trying to solve this issue and finish off the task. So he and his colleague Alfred North Whitehead, they are working on their approach, and they produce 3 volumes of Principia Mathematica. There's the first volume to 56 chapters, and it's well over 1,000 pages. And just to give you an idea of how complicated a task this is, here's from chapter 54 well into 1,000 pages of their work. Statement 43, they give it. You don't have to be able to read what it's saying. I just want to give you the impression that it makes a statement of something and it wants to demonstrate formally that this statement is true. It gives a formal proof and everything's wonderful, right? Very meticulous in its development, so that after 1,000 pages, it's shown this proposition. From this proposition, it will follow, when, of course, arithmetical addition has been defined, that 1 plus 1 equals 2. So that's what you get after 1,000 pages of laying out the foundations of mathematics. Right? Not an easy task, right? But people were trying to do this because it has to be done. Right. I want to turn my attention now, and your attention, to the recognized father of computer science, Alan Turing. There's a picture of him on the new 50-pound note. Right. Now, why I want to think about him? Well, in an absolutely stunning feat of brilliance, Alan Turing devised a thought experiment, essentially about what you could do with a general purpose programming language running on a general purpose computer, and all long before the reality of such things could even be imagined. Yes, and he explained clearly and precisely what constitutes the modern notion of computing and what can be computed. And then he used this to compute the following analogy of Russell's paradox. Now, he spoke about his thought experiment version of computing, but we worded in the modern parlance of a Python program. Okay, Python is a common programming language now. We could use any programming language because this is what a universal programming language running on a universal computer is, right? But he said, suppose we can write the following program, halt. We'll call it halt, halt.py, because it's a Python program, right? And the idea is it's going to tell you if any program that you write will halt or not. You know, you write a program and you run it, and after a while you hope it stops. And maybe you write a program to calculate the average of a list of numbers. So it inputs a list of numbers and then does a little calculation and spits out a number and stops, right? You'd like that. If you're doing that and then you ran the program and you're waiting and you might think, maybe I made a mistake. Maybe my program has accidentally gotten into an infinite loop and it's never going to stop. And you never know whether you should stop the program artificially and look to see if there's an error in it, or you just, maybe I just let it run a little longer, right? Wouldn't it be marvelous if we had another program which we can run and feed into that program, our program, and ask it, is this program going to halt or not? And we'd know whether or not we should just let our program run, knowing that eventually it will halt. Right? So that's what he said. He wants this halting program. So it's a program, we call it halt. And what does it do? Well, it reads two strings, a string P, which itself represents a Python program. So it's going to read a string from a file. It's just going to read text out of a file, and that file is holding a Python program. A Python program which itself has early on a statement that says read a string, right? So this Python program that it reads is a program that takes an input string, okay? And the program halt takes another input, I, which represents a potential input to the program P, okay? And the program halt, what does it do? It looks at the program P and thinks about, if I ran this program P on that input I, would this program halt or not? And if it decides, yes, it would halt, then the program halt returns true. It says, yes, program P on input I halts. Right? But if it looked at the program P and the input I that you'd want to run it on, and it says, well, if you ran P on input I, you'll end up running an infinitely long program. It'll never halt. Then this program will return false. Okay? So it's a simple enough idea as a program. And as I said, it would be a very handy program to have as a computer scientist, just to make sure that the programs you write aren't going to end up in infinite loops, right? Well, if you do have such a program, then here's another program you can write. Let's call it Russell. Okay, and what does the program Russell do? Well, it reads a string P, which represents a Python program, which takes a string as an input. And then it runs the program halt on the input PP. So it's essentially asking halt, if I ran P and fed it as its input string, the program P itself, would it halt? Right? And it says, if halt says it would halt, then I'm going to get myself into an infinite loop. I'll just loop forever and never terminate. So that's what the program Russell would do. It would just run forever. If halt told it that the program P run on input P would halt. But if the program halt said that the program P run on P would not halt, then Russell's going to halt right there, and it'll stop. Okay? So this program Russell is going to halt if the program P run on input P runs forever. And the program Russell's going to run forever if the program P on input P halts. So it's in some sense doing the opposite of what the program P running on P would do. Okay? Now the question. If we take this program Russell and we run it on as input the program Russell itself, what would happen? Would that program halt? If I run Russell on Russell, so Russell takes the program Russell as an input, it runs halt on the program Russell, reading Russell as its input. Halt tells it either that runs forever or it halts. So if it halts, then this program is going to run forever. But if Russell running on Russell runs forever, then this program is going to halt. But hang on, we are running Russell on input Russell here. And this program running Russell on Russell, we're saying is going to loop forever if our halt program says that Russell running on Russell halts. And it's going to halt if our halting program says that Russell running on Russell runs forever. So Russell running on Russell, if it halts, then it's going to run forever. If it runs forever, then it's going to halt. Again, a paradox. Or a paradox? Well, no, actually. It's like, as I say, the Barber Paradox. So if the answer is Russell, run on Russell, halts if and only if it doesn't, we get that paradoxical answer. Of course, we can't really have a paradox. So the conclusion is we can't actually have this program, right? Alan Turing's idea of suppose we had a program that could do it, then we'd run into this paradox. So actually, we can't. We cannot have a program which decides if another given program is input halts. And this is famous now in the subject of computer science as the halting problem. As I said, it's interesting and useful as a result in computer science, right? And it's just a computerization, an implementation, if you will, of Russell's paradox. Now, interesting, but why did this suddenly appear? Let's return back to the problem of mathematics and its foundations. And now we'll introduce this gentleman, David Hilbert. He is perhaps the foremost mathematician of his day, right? And he very much believed in the power of mathematics, and he set the mathematical community a challenge demonstrating that every mathematical truth can be proven, or in his words, decided. This was his Entscheidungsproblem, or decision problem, right? He asserted his belief that any mathematical statement can be proved or disproved, right? So, for example, you might think Goldbach's conjecture that every even number greater than 2 is the sum of 2 primes. So 4, yes, is 2 plus 2, the sum of 2 primes. 6, 3 plus 3, 8, 3 plus 5, 10, 3 plus 7, 12, 3, 5 plus 7, 14, 7 plus 7, and you can go on and on and on and on. And computers have been made to go on and on and on to astronomical distances, showing that Goldbach's conjecture holds for the largest imaginable even numbers, right? But we still don't have a proof that that's always true. But David Hilbert, he very much believed if it's true, there must be a proof. We must be able to prove with mathematics that it's true, right? According to Hilbert, either we can prove this is true, or we can prove that it's false, right? Wir müssen wissen, wir werden wissen. We must know, we shall know. He believed that so strongly that it's on his gravestone. Now, Turing's thought experiment about what can and cannot be computed provided the death knell for Hilbert's dream. Now, Turing didn't devise the halting problem as an exercise in computer science. It would be a fair few years before modern computers in the field of computer science would come into existence, right? He devised the halting problem because of a simple corollary that you can derive from it, that in actual fact, not all mathematical truths can be proven. A simple paradox with such enormous consequences to the whole of mathematics. It just goes to make you think.